You are doing the grouping of cells in series and parallel, right?
Yeah. Yeah.
Now we'll see how we can get the maximum current, because see, this combination of cells is used to provide current to a load resistance, right? Like we have a combination of series where n
Yeah.
cells are stacked up in series. All right, so these are the batteries or cells and the internal resistance, and then they provide current to a load. Okay,
Yeah.
so this will be R1, V1, V2, V3, or let's say E1, E2 up to En, R1,
Yeah.
R2, Rn. This is the load resistance. We need to find how can we get the maximum amount of current from the combination of this cell. Okay, so to do that, let's write the heading: condition for maximum current. So this is the in series, right? So
Yeah.
in series, what will happen? What will be the net EMF of all the cells? And they are connected in series, so they'll add up. So that will be n time of E. If
Upon n times of r plus r.
this all is
Right.
equal to E, then they'll all add up. So n times of E, and net resistance, net internal resistance,
Yeah.
NR.
Into resistance.
If
Yeah.
R1 is equal to R2 is equal to Rn is equal to R. So the current that would flow through the circuit would be I is equal to V by R. Now V is this NE, and the resistance of the circuit is NR plus capital R, correct?
Yeah.
Now there will be two cases. There will be two cases that will use it practically. Practically I'm talking about. So first case is when R is greater than NR. All right.
Well, someone's calling me.
Okay. Okay. Done.
Yeah. No.
Yeah. So
Yeah.
there are two cases when R is greater than NR.
Okay.
That means this load resistance is very large compared to the
Net resistance.
internal resistance.
Yeah.
Then what will happen is the current would be, so this NR can be ignored compared to this capital R in the denominator. We can write this only. Current would be this much. This is approximately, right? So
Okay.
current would be approximately NE by R only. That means, in other words, this current would not depend on R, the internal resistance,
Okay.
correct? Or you can say that, see, each of this cell could give a current of I is equal to E by R,
Yeah.
right? If we
Yeah.
ignore the internal resistance. Now these N cells are giving a current of N times E by R, isn't it?
Yeah.
So we have
Yeah.
got the point that the current would be N times of each cell. Each cell individually would give us, right?
Yeah.
But this is only when R is greater than NR. The second case is R is less than NR. That means this external resistance is very small as
So
compared to the internal resistance overall.
it will
So
be
I would be
Ne upon small r and r.
Ne upon NR, because R would be neglected. This R would be neglected as compared to this
Yeah.
NR. So
Yeah.
N cancels out. So I is just E by R only. Correct?
Yeah.
The current given by the single cell. Now we have got a point to make. The point is, when the external resistance is much higher than the internal resistance. That is the first case, okay? When the external resistance is much higher than the internal resistance,
Transistors. Okay.
then the cell should be connected in parallel to get the maximum current. Because in this case we are getting n times the current, and this current is very small as compared to this, right? So we'll get the, because the heading is the condition for maximum current only. So the current would be maximum when the R, the external resistance, is much greater than internal resistance of all cells. Correct?
Yeah. Correct.
This is the first case. If you connect cells in parallel, oh sorry, series, you'll get the maximum current and R is greater than the internal resistance. Now the second case for the parallel. So for parallel combination, what would happen? Now cells in parallel
Yeah.
connected like this. E1, E2, E3, R1, R2, R3 connected to a load, capital R. So for
Okay.
parallel combination, we know that in parallel the voltage remains the same. So if E1 is equal to E2 is equal to En, this is N, is equal to E, R1 is equal to R2 is equal to R3 is equal to R, then the total EMF would be E only because they are in parallel, and the total internal resistance would be R by N, okay?
Yeah.
Or let's say M, because in case of parallel we took this as M, right? Remember? So this is R by M cells. There's not N cells, they are M cells.
Yeah.
Now the current would be how much? E by R divided by M plus the load resistance. You solve it, what you will get? M E upon R plus MR.
Yeah.
Now here again we'll have two cases. Okay,
Yeah.
so if this R is less than R by M, okay,
Okay.
I mean first case is if R is less than this thing, because these both expressions are the same, right? So
Yeah.
if R is less than this, then what we can do, we can neglect what?
Um, R by no, we can neglect R.
Hmm?
You forget about R.
Mm,
It's less.
we can neglect the R, right? So it would be ME divided by R,
Yeah.
correct?
Yeah.
Is not it M times current of each cell?
Yeah.
Because the current due to each cell is this much only, and we have got M times the current. The second case is R is greater than R by M. In that case, I would be E by R only. Okay?
Yeah.
So in this case, we are getting the opposite. In this case, when R is less than this thing, then we are getting the maximum current. Correct? Or
Yeah.
in other words, you can say when external resistance, okay,
Yeah.
is much smaller than internal resistance, we get maximum current. Correct?
Yeah.
For series it was the opposite. When external resistance was larger than the internal, then we get the maximum current there. But here it's when the external resistance is smaller than the internal resistance. Correct?
Yeah.
So we get the maximum current in parallel combination.
Okay.
So this is the second. Now the third one, when we have a mixed combination. Okay,
Yeah.
so I think we should copy it. Let me see if I can copy it. This. Okay, thank God it is copying today,
Yeah.
because it depends on the computer what the mode is. Sometimes it does not let copy. Anyway, so there are m rows and there are n cells in each row, right? Each of
Yeah.
EMF E and internal resistance R, correct? And the same is
Yeah.
connected to the load resistance R. Now total number of cells would be how much?
N.
What is the total number of cells?
N.
M?
Yeah,
It
because
would
you
be
said
m into
N.
n. N
Oh,
cells
right.
in
Okay.
each row,
Yeah.
then
Because okay.
multiplied by n. Alright?
Yeah. Okay.
Now EMF of each row
Wait,
can,
I have a question.
yeah.
Why are we multiplying instead of adding?
See, these are m rows. 1, 2, 3, 4, 5, 6. It can go up to whatever, and there are n cells in each row.
Oh,
This
okay.
is just like a box.
So, okay. Good.
Like you have m rows and n columns
Okay.
like this, so you will have you not add, it will count only
It will be
these
wrong.
only.
Right. It will be okay. Oops. My bad.
So emf of each row, what would be the emf of each row of n cells? It would be ne. Okay,
Yeah.
now m such rows are connected in parallel, right?
Yeah.
M such rows are connected in parallel, and we know in parallel, how no matter how many cells you connect, the EMF still remains the same. It would be still NE, isn't it?
Yeah.
I mean to say the combination EMF, the total EMF would be NE only, correct?
Yeah. Yeah.
Now let's talk of the internal resistance. So internal resistance of each row would be how much? NR, correct?
Yeah.
Now M such rows are connected in parallel. So when resistance are connected in parallel, what would be the total resistance? Internal
Uh.
resistance
E.
of M such rows. You know, when let's say there are many resistance of the same value, let's say R, R, three resistances are connected in parallel. What would be the combination? What would be the equivalent resistance? R by
Uh.
3, okay? R by 3. You calculate it using 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3, correct?
Yeah.
You will get R by 3 because there are 3 resistances of the same value.
Yeah.
So if
Okay.
there are M resistances of same value,
So it'll be.
this would be like this.
Yeah.
NR divided by M. Now we can find the current. So the current would be the EMF, which is NE, divided by the total resistance NR upon M plus the load resistance. Alright,
Yeah.
now let us solve it a little bit. When you take the LCM, you will get M and E on the numerator divided by NR plus M capital R. Alright,
Yeah.
now when will the current be maximum? Current is maximum when, see, this is numerator, this is denominator. So the fraction is maximum when the numerator is denominator
Greater.
is bigger or small.
When the numerator is bigger.
Denominator I'm talking. If this
Small.
is small, this would be large because they are inversely
Yeah.
proportional, right?
Yeah.
See, this E has nothing to do, it is already a constant. That's why we are not talking about the numerator. This is
Oh, okay.
variable, no? So that's why we
Yeah.
need to talk about. If this is small, the current would be maximum. Now we need to make it smaller. So what he did is he did something. It will not come in exam actually.
Okay,
The
so
correct way
yeah.
to do it is with the differentiation. The one that we are just studying.
Okay.
But there
Yeah.
are some other way around also. Sometimes, not every time, you can get the answer with other ways. So by calculation, what he has found is we will get the maximum current I max when this R is equal to NR divided by M. Okay,
Yeah.
that is R should be equal to the internal resistance of the cell of the combination, isn't it?
Yeah.
So that is what it is. R should be this. I'm not doing the analysis because that will not come anyway.
Okay.
Now let us do a question or two on this. So example 87. It's very easy, you can do it on your own. Do it as a homework. 87 and 88.
87, 80. Okay.
And that's it.
Okay. I'll leave.
What?
I said I will leave.
No, we'll do something else also.
So,
We'll start with the heating effect of current also.
oh, okay.
Heating effect of current. So it's very easy. Already done most of it in class 10th already. When the
Okay.
current passes through a resistance,
Yeah.
it produces heat.
So,
Depend on the type of resistance, what it is metal, like copper or something, iron, or it is some nickel, or it is some tungsten type material which is used in heaters. All right,
yeah.
these are all some types of resistances, some materials. When current passes through resistance, it is produced, and that is given by heat. So heat is in fact the energy, you know, the heat or the energy that will be consumed is equal to I square R into T, the time for which you want to find the consumed energy. Okay,
Yeah.
this is the formula, and the SI unit is joules. Okay.
Yeah.
What is the power? Power is
Power.
I square R, alright, or
Okay.
I into R, or P square upon R. You might already know this,
Yeah.
right? Similarly, heat is V into I into T, or I square RT, V square by R into T. Power is given in watts. Okay.
Yeah.
Now, this watt is a very small unit of energy. Commercially, more bigger units are used. For example, kilowatt. So 1 kilowatt is equal to 1000 watts, or even 1 megawatt, 10 to the power 6 watt. Correct? And there is
Yeah.
another unit of power which is horsepower. HP is equal to 746 watts. Correct?
Yeah.
Now, this is the unit of power. Similarly, equivalent to this, so this is the unit of power, we have a unit of energy. Correct?
Yeah.
So Energy corresponding unit can be, joule is in fact watt into seconds.
No. I think we were great then.
Yeah, because you are just multiplying power with time, isn't it?
Yeah.
So the unit should be watt into second. But commercially, the energy units are not just watt into second or joules. What we use is just the kilowatt hour. Okay,
Okay.
correct.
Uh,
And if you find how many joules it has, you can just find by substituting the values. So 1 kilowatt hour would be 1 kilowatt is 1000 watts, and 1 hour is 60 minutes, and 1 minute is 60 seconds. Now we have converted into watt second, which is joules, correct?
yeah.
So this would be 3.6 into 10 to the power 6 joules. And this 1 kilowatt hour is also called 1 unit of energy. So
Okay.
when what you get in bills, electricity bills, you
Yeah.
say that we consume 200 units of energy, so that is
Yeah.
200 kilowatt hour in fact.
Um,
Okay,
but,
unit is has been given a general name. The unit means the kilowatt hour only, correct?
yeah.
So that something about energy. Now let's talk about the power when the appliances are connected in series or parallel. Okay, so
Okay.
power in series and parallel combination. Suppose n bulbs are connected in series. Okay,
Yeah.
n bulbs are connected in series, each consumes power P1, P2 and P3. Okay, and the potential
Yeah.
difference is the V volts. So when you find a bulb on the package,
Yeah.
this is the bulb, this is the filament, these are the two terminals. Now on the package you would find the voltage rating of the bulb,
Yes.
that is given in volts. So let's say the voltage rating of this bulb is V volt, and the same bulb we are using, so each one of them has a rating of V volt, correct? Most
Yeah.
generally it is 220 volts, correct,
I
isn't
don't
it?
know, but yeah.
It is generally 220. In the charger also, on the Apple charger, you can see the voltage rating. So
Okay.
the question is not what we are doing. The question is what would be the equivalent power consumed by the total combination. All right.
Okay.
Is it P1 plus P2 plus P3 or what?
Uh, um, P1 plus P2 plus
No,
P3
you
over the whole thing.
power equivalent is what? To your surprise, it is not P1 plus P2 plus P3.
Um,
You can find that. How? See, let's calculate the resistance of each one of them using the power rating, right? So the resistance of R1 would be V square by P1, isn't it? How?
yeah.
Because power is how much? V square by R, then R would be
Right. Okay. Okay.
V
Yeah.
square by P. Why we are not using the other formula? Power is also I square R. Because
Because
I
of
is
your
the current rating is not given, the voltage rating of the bulb is given. So R1 is this. Similarly R2 would be V square by P2, R3 would be V square by P3. Okay.
Yeah.
Now if you want to find the effective combination, R equivalent would be how much? R1 plus R2 plus R3. Correct?
Yeah.
So now let's calculate that. You will get V square by P1 plus V square by P2 plus V square by P3. This is the R equivalent,
Yeah.
and this R equivalent is equal to V square 1 by P1 plus 1 by P2 plus 1 by P3. Alright?
Yeah.
And what would be the R equivalent? Tell me.
Uh,
R equivalent would be V square upon power equivalent, isn't it?
yeah.
So let's replace R equivalent with V square upon P equivalent is equal to V square 1 by P1 plus 1 by P2 plus 1 by P3. V square cancels out. What you get is 1 by P equivalent is equal to 1 by P1 plus 1 by P2 plus 1 by P3. This is the formula for equivalent power in series as opposed to the resistance, because this is what the resistance in parallel looks like, isn't it?
Yeah.
But the power case, it's the opposite. Remember, it's a series combination and it's giving us a parallel power, like a parallel combination of
Yeah.
resistance.
Okay.
Now
Okay.
what, so for parallel, what would happen if the same bulbs are connected in parallel? What would be the effective power? Now in this case it will be the sum of all, is P1 plus P2. You can easily verify that also, but I'm not doing it. This will not come in exam, neither this will come. Okay, what you need to
Oh,
know is this, the final result.
it's not going in exam.
No, but the application of this will come, the final results application will come. That's it. Not the derivation would want. I'll tell you which derivation might come, which might not.
Okay. Because there are so many derivation.
Yeah, there are.
And we're
What
only on the third chapter. And it's a lot.
I'm telling you, don't do only those which I tell you to do.
Okay.
Now another thing to note, see in the series combination, these bulbs are connected, the current will flow I. Can we find this
Yeah.
I? So
Yeah.
this I would be what? V
Uh,
upon the
R.
equivalent resistance.
Yeah.
So R1 plus R2 plus R3.
Yes.
R1, this would be the current, right?
Yeah.
Now this current is I. Now if you want to find the brightness of each bulb,
Oh, okay.
so see, the power equivalent is 1 by P equivalent is 1 by P1 plus 1 by P2 plus 1 by P3.
Yes.
So in a series combination, the bulb of lowest wattage, okay, will glow maximum brightness.
The bulb with lowest. Okay.
Bulb of lowest wattage will go to maximum brightness. Why? Because the lowest wattage bulb, right, will have a maximum resistance. Okay,
Yeah.
the lowest wattage bulb, suppose, you know, I'll tell you some other time. For the time being, you can just remember this thing and this thing. The lowest bulb will grow maximum. Okay, but for the parallel, the bulb of maximum power will grow brighter. It is understood also, no? Because,
Yeah.
yeah, you can see in your homes, different bulbs are connected in parallel. That is understood. In homes, there is no series connection. Whatever connection is there, that is everything is in parallel. Okay.
Yeah.
For example, kitchen bulb, washroom bulb, everything they are in parallel. So as you increase the wattage, for example, you get a 200 watt bulb, and then you have a 10-watt bulb, or you also call it 0-watt bulb, which is not a case. Zero is not anything, but you buy from the market and tell the shopkeeper to get a 0-watt bulb, he will give you. Zero
Oh.
means just the minimum wattage. Okay, so
Okay.
if you connect,
Wait, so the 0 watt bulb is the, well, like the colored ones, like
yeah,
red.
those ones, yeah, those are called 0 wattage bulbs. So those glow very with very less intensity or brightness, correct?
Yeah.
But as you grow the wattage, you get a 200-watt bulb, it will grow brighter because they are in parallel. Okay,
Okay.
this is the practical example. Maximum power bulb will grow brighter in a parallel combination. I cannot give you an example of a series combination because it's not found in homes. In homes, we connect everything in parallel. So whatever has the maximum power, that one will glow brighter.
Okay.
Otherwise, you can think like this, na? Since this is a very low wattage bulb, this has a less resistance, and this is a high power bulb, this has a more resistance,
High
isn't it?
resistance. Yes.
Then what the hell? It does not grow brighter. It has a less resistance. It should glow more than this 200-watt bulb, isn't it?
Yeah.
One can also think like this. But it is because the
Uh,
parallel combination,
the less resistance.
whatever is
Very.
bigger, it will grow brighter. That's it.
Okay.
Okay, so I think what else? I think that's it for today.
Okay.
Okay. You can do some questions from the book.
Okay. Will I take class tomorrow?
Yeah, most probably. Yes. Okay, all right.
Okay then. Oh, wait. Can